All right, here's where we, excuse me, here's where we left off from part one. And I did change it a little bit, so hopefully it's a little bit easier to see. We came up with a sample space from this chart when we were flipping a coin 3 times. So we've got first flip, second flip, third flip. And just to go over this again quickly, when you flip it the first time, you're either going to get a heads or a tails. And then from there, depending on what you get, you're also going to get a heads or tails. So second flip, if you got a heads, whenever you flip it again, you're either going to get heads or tails. If you got a tails, when you flip it again, you'll either get a heads or a tails. And then depending on which outcome you got here, you get heads or tails either way again on your third shot. So we can see that we should have a total of 8 outcomes, 1, 2, 3, 4, 5, 6, 7, 8. And then if we follow these different paths, we should get all the different outcomes that we have. So first flip heads, second flip heads, third flip heads, that's this one. First flip heads, second flip heads, third flip tails, HHT. So that's where I'm getting all these. Let's see, tails, 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 that'd be right there, that last one. Tails, heads, heads, right there. So that's how we're getting all those outcomes. So we, or at least I predicted that we will get heads at least once, as opposed to not getting a heads at all, or not getting it at least once. So let's see what our actual probability of getting heads at least once is. So if we get a heads at least once, we should see it at 1H in here. So 1H or more, we're going to underline. We got 1H there, or 3 here, 2 here, 2 here, 1 there, 2, 1, 1. And the only one that we don't have at least 1 heads is the last one where we get all tails. So the probability of getting at least 1 heads would be 1, 2, 3, 4, 5, 6, 7 out of 8. And the probability of not getting a heads, we should be able to just take 1 minus 7/8 to get our answer. It should be 1/8, but let's make sure that's true. That's the only one that doesn't have a heads in there, so 1/8 of a chance of not getting heads for that one. So that's how we go about this problem, and we can see that this diagram definitely helped us out and able to organize and figure out our sample space, and then figure out the probabilities for each of those. So it looks like that prediction was right, as it should be. We'll move on. Alright. Last thing we need to cover. We need to talk about theoretical probability and experimental probability. And I'll try to make this easy so that we can distinguish between the two. Theoretical probability, by definition, is found by analyzing a situation. Experimental probability is determined statistically. So they're going to talk about experimental here quick. Experimental probability is the ratio of the number of times an event occurs to the number of trials. So here's some examples here. If a basketball player makes 80 free throws in 100 attempts, then the experimental probability of that player making a free throw is 80 out of 100. So that would be how many favorable outcomes there are, 80 makes, over the amount of attempts or trials. So 80 out of 100, which reduces the forfeits. Alright, so we might say that that player is described as an 80% free throw shooter. So also that last little part there, in baseball and softball, a player's batting average is the experimental probability, and we express that as a decimal, which we will see on the next problem. So the best way to go about thinking about the difference between the two is remember that for experimental probability, you get that from some sort of experiment or from actually observing what's happening. You're going to look at the number of outcomes versus how many total trials there are. So you'll be looking for how many hits somebody got and how many at bats, or how many free throws they made and how many attempts they made at a free throw. Things like that. Or how many flips you get when you do, or how many tails you get when you flip a coin 10 times, something like that. Now let's just think about that, just flipping a coin. Let's say we flip a coin, So flipping a coin 4 times, that would be an experiment. So theoretically, how many heads and how many tails would you expect to get? Well, in theory, we would expect two tails and 2 heads. The reason we would expect 2 tails and 2 heads in 4 flips is because you have a 50-50 shot of getting a tails or a heads because there's only 2 outcomes or 2 possibilities there. So in theory we would expect to get 2 tails and 2 heads, or see our probability be 50% basically. But experimentally, if we do an experiment and we actually flip a coin 4 times, if I gave each student in my class a quarter and told them to record what they got for each flip, I might get, 1 heads and 3 tails over here. I might get 2 and 2 over here. I might get all 4 heads. I might get all 4 tails. You don't know what you're going to get in an experiment. So experimental probability comes from observing a situation. Theoretical is what we would expect to get by analyzing the situation. So that's kind of the difference between the two. Now the thing about experimental probability, let's say we increase this to a bigger number. Let's say we flip the coin 500 times. Okay? The more trials that we have in an experiment, the more or the closer we're going to get to a theoretical probability. So we would expect about 50% heads, 50% tails here. The more this number increases, the more times you do a trial, the closer you get to that actual theoretical probability. And we'll be talking about that in the future. But that hopefully helps us cover the difference between the two. Okay. Last question here. We're going to talk baseball, and they express averages differently, baseball and softball. So it says Emily is a softball player who has 21 hits in 60 at-bats. Express the probability that Emily will get a hit in her next at-bat as a decimal number with 3 decimal places. Okay. So let's take a look. She's got 21 hits in 60 at-bats. So 21 favorable outcomes in 60 attempts or trials. So this would be an experimental probability. And we're going to divide this. 21 divided by 60 because they want it as a decimal. So we're going to go 60 and 21, and we want 3 decimal points. So 3 decimal spots. 1, 2, 3. 60 goes into 21 0 times. I'm not going to put the 0 because in baseball or softball, batting averages are usually expressed without a 0 in the ones place. That's our ones place. We're not going to put anything there. Normally we would. Alright. 60 goes into 210 3 times. 3 times 60 is 180. And I knew it was less than 4 because 4 times 60 is 240, which is bigger than 210. So we'll do our subtraction. 11 minus 8 is 3. We're going to drop down our 0. 60 goes into 305 times. Exactly 5 times. Drop this down. 0. 60 goes into 0 times. So Emily's batting average is 350. Now don't be confused when I say 350. That does not mean 350. In baseball slang they say 350, but this is actually 35 hundredths because the 5 is in the hundredths place. But they would call this 350 in the batting average world. So she's batting 350, not to be confused with an actual 350. Alright, we found her average, and now Emily's coach needs to decide whether to have Emily bat or to use a substitute hitter whose batting average is 300. Alright, and how would we advise the coach? Well, I think we'd rather have somebody up the bat that's a 350 hitter as opposed to a 300 hitter. And once again, this is actually 3500ths. This is 3/10ths. Either way, this number is bigger. So we want Emily to bat because she has the higher average. And I think that's all I have today. So we'll continue with this tomorrow, and we'll see you then.